This is Number Theory, Lecture 6. And what we proved in the last lecture were two fundamental results. One has the name fundamental. The fundamental theorem of arithmetic, which I often abbreviate by FTA, which says that every positive integer is uniquely up to order the product of prime numbers. And the second theorem, which goes back to Euclid, says number of primes is infinite. There are infinitely many primes. Now, what are hard problems and I'll write, that means that these are algorithmically unsolved. So this is really something that only makes sense if you studied a little bit of computer science. Two hard problems, right? Factoring. Given an integer, write it as a product of primes. Factor the integer. Or you might say, if I give you some big number, suppose I take n to be equal to 378997100263519. Write that as a product of primes. Well, there are only finitely many numbers smaller than this. You divide each of them into n, and eventually you'll start factoring the number. But for numbers that are really big, if you try to do this with the fastest supercomputer ever constructed, the sun will burn out before you get the factorization in many cases. So by saying it's algorithmically unsolved does not mean that it requires an infinite amount of computation to solve the problem. It only requires a finite amount, but that finite number is so big, it's effectively impossible to do. And the second problem is to find large prime numbers. So if you want to find a prime number bigger than 100, that's not too hard. If you want to find a prime number bigger than 100 million, it's not too hard. If you want to find a prime number bigger to 100 million raised to 100 millionth power, that's really impossible on any computer that we have today. And another problem which is hard is to find prime numbers of a simple form. For example, primes which are a square plus 1, e.g. So for example, 5 is 2 squared plus 1. 17 is 4 squared plus 1. 37 is 6 squared plus 1. 101 is 10 squared plus 1. 197 is, I think, 14 squared plus 1. So there are a lot of primes which are a square plus 1. And why is this interesting? Because a number that's a square is obviously not a prime. It's divisible by n. But if you take this number n squared, which is clearly composite, and you just add 1 to it, maybe it becomes a prime. So the question about n squared plus 1 is, are there infinitely many primes that are the form n squared plus 1? You might say, what about n squared minus 1? But of course, n squared minus 1 is not a prime because n squared minus 1 factors n plus 1 times n minus 1. But n squared plus 1 is a much, much harder situation. For relatively small numbers, I mean, this number, let's see, thousands, millions, billions, 378 trillion, 997 billion, 100 million, 263,519. It's not that small, but it'd be very hard to factor this by hand. Maple can actually do numbers of this size. Let me open a Maple window and see. Let me share the screen with this. So I hope you can see the screen. And let me just make a note. The way you write a note in Maple is to precede it with a sharp sign, but for some reason this doesn't seem to want to work. I don't know why. There it goes, definitely. Okay, so some number theory commands. So the command to factor an integer into a product of primes is I factor. And then you, in parentheses, you type in the number n that you want. So let's look at this big number I just wrote down. I factor the number 378,997,100,263,519. Oops, I put the wrong parenthesis. Let's try it now. Okay, so this big number is a product of these 4 distinct primes. Okay? I mean, Maple just does it. Let me put a bigger number in. Let's see. Suppose I add some digits to this number. Let's see, that's pretty big. Oh, wow. Maple factored that guy. That's pretty impressive. And it has one very small prime, 61, but these primes are humongous. Let's see if I can stump Maple. Yeah, that's a much bigger number. Can Maple factor that? Let's see. Oh my God, wow. So somehow this number is divisible by 31, but this guy is supposed to be a prime. Let me just check. There's a command in Maple called isPrime, and it's like you're making the statement, is this number is prime, true or false? And this is true. Wow. So Maple could factor this. I'm going to make the number even bigger. I'm just hitting keys at random. Ah, now it's not working. It's trying. This symbol means that it is computing and it's in a kind of a loop. Huh. That's too big. Oh, no, it did it. Wow. It took a while. So this number is actually divisible by 3 and by 9 and by 7 and by 49. And then, so this is 3 squared, 7 squared, this times this times this. I would have thought this would be too big. Is that okay? Yes. So this guy actually factors. Wow. Okay. Any questions about that? It's really quite interesting. So Maple is pretty powerful. But this is not what you would call, even though it's huge, this is not what you would call an industrial grade prime. In fact, how big is it? How many? Suppose I take the log of this number. Huh. Why doesn't it want to give me the log? I'm going to get some help here. So the log, the common logarithm is ln log to base 10. That's what I want in this case, actually. So let me write this as log 10 of this number. Huh. Doesn't seem to be able, maybe this is just too big. The natural log of that number. Huh. So Maple doesn't seem to be able to calculate this. Let me just remove some digits. That's a little smaller. Still can't do it. I got some more digits. Huh. Maybe what I need to do is compute this as a decimal. Ah, okay. So this original number, if I take the log, the natural log, it's 145. If I take the log to base 10, log 10, so this number is like 2 to the power 62, almost 2 to the power 63. That's a pretty big number. But Maple did factor it. That's really quite remarkable. And suppose we want to compute prime numbers of the form n squared plus 1. So to do that, I can write a loop. So if you know Maple, you can do this. And if you don't know maple, at least you'll see the result. Let's say I want to look at, so n squared plus 1. Suppose I let n go from 1 to 100. For n from 1 to 100 do. And then a do loop in maple ends with n do. And I'm interested in knowing whether n squared plus 1 is a prime. So I can put in a conditional if is prime n squared plus 1, then print n and n squared plus 1. And if. So this is going to look at n squared plus 1 for all n's from 1 to 100 and print out the result if it's a prime. So here, when n is 1, we get 2. When n is 20, we get 401. Now you should notice that except for n equal 1, the n's are all even. And that's because if n is odd, n squared is odd, n plus 1 is even, so it can't be a prime number. So it's sufficient to look just at even n's. So if I forget the prime 2, I could say for n from 2, and instead of wasting computing power, I can just go up by 2. That means just look at the numbers 2, 4, 6, and so forth, and we get the same result. There are a lot of these guys. We want to go up to 500. Ooh, there are a lot more. It looks like there are a lot of numbers of the form n squared plus 1. Computer is really good for doing these kinds of experiments. Any questions about this? Let me just save this. So we can stop the share. Any questions about any of this? This is really very interesting arithmetic. Okay. There's one more classical result that goes back to the Greeks, which is an algorithm, a method to compute by hand or by computer prime numbers up to a certain point. Supposing so long as the point is not too large. And this is called the sieve of Eratosthenes. This is in the text in section 1.5. So let's start by looking at the proof of Euclid's theorem that there are infinitely many primes. Suppose we let P1, P2, P3 up to P sub k be any finite set of prime numbers, let capital N be the product of all these numbers plus 1. So N is at least 2, which means N is divisible by some prime number Q that is, if Q is equal to P sub I, if it's equal to one of these primes, for some I between 1 and K, then Q divides N, and Q divides, if it divides one of the P's, it divides the product of all of the P's. So Q divides the difference, N minus P1, P2, up to P sub K. But that difference is equal to 1. And 1 is not divisible by a prime. This is impossible. This is absurd. So we have a contradiction. And we conclude that there exists a prime Q different from P sub I for all I going from 1 up to K, which means given any finite set of primes, there exists a prime that does not belong to that set. Therefore, the number of primes cannot be finite, because if there were only finitely many primes, we would write them all down, multiply them together, we get a number, a big number, but just a number, add 1, and this number, capital N, would have to be divisible by a different prime, not one of these. But we said these were all the primes, and that's absurd. So this is Euclid's proof that there are infinitely many primes. The Greeks, very clever people, made another observation about the primes. So let N, at least 2, be composite. That means it factors. So then N can be written as A times B, where both A and B are at least 2. This is a non-trivial factorization. It's not 1 times N. If A is bigger than the square root of N, and B is bigger than the square root of N, then AB is bigger than the square root of N times the square root of N, which is N, but N is equal to AB, and we would have a contradiction. This says N is strictly bigger than N. That's absurd. So if N factors, so our conclusion, if N factors, then one of the factors is at most, that means less than or equal to, the square root of N. If they were all bigger than square root of N, so the product would be. And we can extend this if N factors into a product A1, A2 up to A sub K, then where K is at least 2, then A sub I is at most the square root of N for some I. So in particular, if N is composite and N factors into a product of primes, not necessarily distinct, say a product of K primes, then P sub I is at most the square root of N for some prime dividing n. So I can state this if I like as a theorem. Every composite integer, positive integer at least 2, is divisible, every composite integer n is divisible by a prime p, which is at most the square root of n. So if a number is composite, if it's not a prime, it has to have at least one small prime factor, where small means less than the square root of n. And if we're interested in all the prime numbers up to some number x, every composite integer n less than or equal to x is divisible by a prime number p, which is at most the square root of x. Because every n will be divisible by a number at most the square root of n, and if n is less than x, square root of n is less than the square root of x. So this is the idea of the sieve of Eratosthenes. So the idea of this sieve. Fix x. So we have the problem. Find all the primes p less than or equal to x. If a number n is composite, if n is less than or equal to x, then p divides n for some prime p at most the square root of x. So take all the numbers, write down all the integers from 1 to n, cancel, cross off all multiples of p for p from 1 to the square root of x. What's left are the integers p between the square root of x and x. So the easiest way to understand this is by example. So here's a problem. Find all primes less than or equal to 60. So what we do is write down the numbers from 1 to 60. So it takes a few seconds. Almost there. So here we have all the primes up to 60. No, I just see something in the chat about maple. So, so when I'm showing you something in maple, I'm not requiring that you learn maple and can do what I'm showing with maple. If you do know maple or are studying maple, then you'll see some commands for how to do programming in maple to solve some problems in number theory. If you don't have maple, don't know maple, again, what's important is just to see how a computer can solve these problems with relatively simple commands and to see what the solutions are. But I'm not going to ask you to take a test on maple. That's purely sort of enrichment if you're interested. And if you are interested, I have a lot of videos of lectures on how to use maple posted on YouTube. And you can always ask in a problem session. There are problem sessions today at 7, tomorrow at 7, Wednesday at 7 at least. Anyway, here we have the numbers from 1 to 60. So I have to, first of all, step 1, list the primes less than or equal to the square root of 60. Well, square root of 60 is between 7 and 8. The primes less than the square root of 60 are 2, 3, 5, and 7. So I want to find the primes on this list, and I'm going to cross off the multiples of 2, 3, 5, and 7, except 2, 3, 5, and 7, which are primes. So first of all, 1 is not a prime. I cross that off. So now I want to cross off the multiples of 2. I don't cross off 2. 2 stays. But then what are the multiples of 2? They're all the even numbers, 4, 6, 8, and none of them is a prime. So I'm crossing them all off. Now, crossing it off means divisible by 2, not a prime. So I'm really crossing off half the numbers right away. What's the next prime? 3. I don't cross off 3, that's a prime, but every multiple of 3 is composite. So I cross off the multiples of 3, 6, 9, 12. You'll notice some numbers, the even numbers, I'm crossing off twice, that's okay. 15, 18, 21, 24, 27, 30, 33, 36, 39, 42, 45, 48, 51, 54, 57, 60. So I crossed off the multiples of 3. The next prime is 5. Here's 5. And now I cross off the multiples of 5. 10, 15, 20, 25, 30, 35, 40, 45, 50, 55, 60. The last prime is 7. There's 7, but what are the multiples of 7? 14, 21, 28, 35, 42, 49, 56. So I've crossed off the multiples of all the primes less than the square root of 60. What are the numbers that are left? 11, 13, 17, 19, 23. These are all primes. It's a miracle. 31, 37, 41, 43, 47, 53, 59. So on this table, every number is either crossed off or it's circled in red. And the ones circled in red are all the primes up to 60. So if I want to list the primes less than or equal to 60, they're just the primes that are circled. 2, 3, 5, 7, 11, 13, 17, 19, 23, 29, 31, 37, 41, 43, 47, 53, 59. There's 17 of them. We define the counting function for the primes. Pi of x is the number of primes p less than or equal to x. So what we just proved is that pi of 60, the number of primes up to 60, is 17. Any questions about this? Let's look at some of the problems involving prime numbers. So in section 1.5, the first problem is to use the sieve of Eratosthenes to calculate all the primes up to 210. So that's a little bit longer calculation than the one we just did, but it still is doable by hand. And then using that, problem 2, well, that requires that you've done problem 1, that you know the primes up to 210. Let's look at, in section 1.5, number 3. So in problem 1.5, section 1.5, number 3, you take the number n to be 105. And we want to show that n minus p is prime. Sorry, not n minus p. That n minus a power of 2 is prime for all n such that 2 to the n is strictly less than n, equal to 105. So what are the powers of 2 less than 105? 2, 4, 8, 16, 32, and 64. The next power of 2 is 128, which is too big. So let's make a table. Here's n, and this is capital N, 105 minus 2 to the n. So for n going from 1, 2, 3, 4, 5, 6, and then we make a table like this. This will be 2 to the n, and this will be 105 minus 2 to the n. 2, 4, 8, 16, 32, 64. 105 minus 2 is 103. 105 minus 4 is 101. 105 minus 8 is 97. 105 minus 96 is 89. 105 minus 32 is 73. 105 minus 64 is 41. And you can check, these are all prime. So this integer 105 has this curious property that you can write it as a power of 2 plus a prime for every power of 2 that you could possibly use. Right. Any questions about this? Let's see. Someone said I have the wrong number for the number of primes up to 60. So let me just double check. 2, 3, 5, 7, 11, 13, 17,
Professor.
19, 23, 29, 31, 37, 41, 43, 47, 53, 59. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Did I miss one? Seems to be okay. I don't see any prime that I might have missed. Okay.
Professor,
Yeah,
for this question right here, you said the answer was 41, right?
for this problem,
Yes.
um, no, the problem doesn't ask you to find a number. The problem is just to show, do a calculation to show that n 105 minus 2 to the n is a prime for all powers of 2 less than 105. So these are the powers of 2 less than 105. When I subtract these numbers from 105, I get these 6 numbers, and these are all prime. So it's not this is just an exercise to verify this statement, right? Show that 105 minus 2 to the n is prime for 2 to the n less than capital N, and so I do the calculation, and these numbers are all prime.
Oh, okay, okay, I understand.
Let's look at problem number 5. Suppose we have A and N positive integers. Prove that if the number a to the n minus 1 is prime, then it must be the case that the number a is prime and the exponent n, that the number a is equal to 2. The only way this is prime is if a is 2 and n, the exponent, is prime. So why does a have to be 2? So a is a positive integer. If a were 1, this would be 0, which is not prime. Why does a have to be 2? Well, suppose it's bigger. If a is greater than or equal to 3, then you can factor a to the n minus 1. This is a minus 1 times 1 plus a squared up to a to the n minus 1. So you have to know this factorization formula. So if you haven't known it up to now you know it. I mean, the simplest case you learn in already. A squared minus 1 is a minus 1 times a plus 1. A cubed minus 1 is a minus 1, or I can write this as in the opposite order, it doesn't matter. A squared plus a plus 1. A to the fourth minus 1 is a minus 1 times a cubed plus a squared plus a plus 1. So in general, a to the n minus 1 is divisible by a minus 1, which is bigger than 1 if a is bigger than 2. So if a, and this number is 1 plus something, this is bigger than 1. So if a is bigger than 2, that means greater than or equal to 3, a to the n minus 1 is composite. So the only time a power minus 1 can be a prime is if you're taking a power of 2. So we're only looking at numbers of the form 2 to the n minus 1. But suppose n is composite. That means I can write n as r times s, where r and s are both bigger than 1. So this is 2 to the rs minus 1, if n is equal to rs. And 2 to the rs is the same as 2 to the r to the s minus 1. R is at least 2, s is at least 2. So here I'm taking a power of 2 to the r, which is bigger than 2, and then this also factors. This is 2 to the r minus 1 times 1 plus 2 to the r, 2 to the r squared, and so forth. This factors. So if the exponent n is composite, again, this number factors. So the only possible way a number 2 to the n minus 1 is prime is if the exponent is prime. So this is a very good argument, a very interesting proof that uses what is basically high school algebra, but in a somewhat sophisticated way. But it depends on knowing this factorization formula, that you can factor a to the n minus 1. And again, let me just write it down again, because so a to the n minus 1 is equal to a minus 1 times a to the n minus 1, a to the n minus 2, decreasing powers of a squared plus a plus 1. This is a fundamental factorization formula in algebra that you need to memorize. You really need to know it because it comes up constantly, and certainly in algebra and number theory and elsewhere in mathematics as well. So if a to the n minus 1 is prime, then a is 2 and n is a prime number. So our prime is really of the form 2 to the p minus 1. So a prime of this form, so if this number is prime, it's called a Mersenne prime. Mersenne was a Jesuit priest a couple hundred years ago who discovered all of this. Let's see. Let's just do some little experiment. Compute p and then 2 to the p minus 1. If p is 2, 2 squared minus 1 is 3. That's a prime. If p is 3, 2 cubed minus 1 is 8 minus 1 is 7. That's a prime. P is 5, 2 to the 5th minus 1 is 31, which is also a prime. If P is 7, what is 2 to the 7 minus 1? 2 to the 7th is 128 minus 1 is 127. I think that's also a prime. So the first few numbers of the form 2 to the P minus 1 are primes, but not all numbers of the form 2 to the P minus 1 is prime. And it's an open problem for 100 years. Are there infinitely many primes? So here we're looking at powers minus 1. In the next problem, problem 6, in section 1.5, we look at powers plus 1. And we have to prove the following. It says let K be a positive integer prove that if 2 to the K plus 1 is prime, so if a power of 2 plus 1 is prime, then the power itself, K, has to be a power of 2. So the prime would be of the form 2 to the power 2 to the n plus 1. It's like a double exponent, or this f sub n. And a prime of this form is called a Fermat prime. Fermat thought that every number of the form 2 to the 2 to the n plus 1 might be prime. And this was an unsolved problem for a long time. And then it was solved, and Fermat was wrong. Not every such number is prime. But how do we prove this statement? This is what we have to prove. If 2 to the K plus 1 is prime, then K is a power of 2. And it comes down to another factorization formula. When can we factor x to the K plus 1? Right. For what K is this possible? So x squared plus 1 does not factor. What about x cubed plus 1? This does factor, I think. This is x plus 1 times x squared minus x plus 1. So you might, let's just pause for a moment, take a piece of paper, and check that this is true. Just multiply this out. If you multiply it out, you get x times x squared minus x plus 1 plus 1 times x squared minus x plus 1. This is x cubed minus x squared plus x squared minus x plus 1. And you see the minus x squared and the plus x squared cancel. The plus x and the minus x cancel. You're left with x plus 1. So x squared plus 1 does not factor. X cubed plus 1 does factor.
You mean you're left with x cubed plus 1, right?
Yeah. So this times this is x cubed plus 1. So x cubed plus 1 does factor like this.
Okay.
What about x fourth plus 1? X squared plus 1 factors x cubed plus 1. It does not factor. X cubed plus 1 does factor. X4 plus 1 also does not factor. What about x to the 5th plus 1? Well, this, in fact, does factor. This is x plus 1. X to the 4th minus x cubed plus x squared minus x plus 1. That factors. X to the 6th plus 1 does not factor. But x to the 7th plus 1, I can factor that. That's x plus 1. X to the 6th minus x to the 5th plus x to the 4th minus x cubed plus x squared minus x plus 1.
All the even x's does not factor.
Right, exactly. So we can say the following. If k is odd, an odd positive integer, and x to the k plus 1 will always factor into x plus 1. And then we have this alternating sum starting with the power k minus 1. You get a factorization like this. This is always true if k is odd. So suppose we consider the number 2 to the k plus 1. So if k is not if k is odd. Let me write this down. Let's look at this number 2 to the n plus 1. If n might be even or odd, but if n has an odd factor, k, so n is equal to, let's say, m times k, where k is odd, then 2 to the n plus 1 is 2 to the mk plus 1. 2 to the mk, just by rules of exponents, is 2 to the m to the k plus 1. So this is of the form x to the k plus 1, where x is 2 to the m. And so then this factors, because if k is odd, this factors. This factors into x plus 1, 2 to the m plus 1, times another factor that's 2 to the m times k minus 1, alternating signs down to 1. This is a factorization. So if n has an odd factor, this number is composite. It factors. If n has no odd factor, when you factor n, it can only be a power of 2. So it's only my notation is a little bit different from in the notes. So if we have 2 to the k plus 1, if k has no odd factor, that means k is just a power of 2, number of the form 2 to the n. So this is 2 to the 2 to the n plus 1. So 2 to a power plus 1 is a prime only if the power itself is a power of 2. So we have this double exponent, 2 to the 2 to the n. 2 to the power 2 to the power n plus 1. And we have a prime number. If 2 to the n plus 1 is prime, it's actually the form 2 to the 2 to the n plus 1. But not every number of this form is prime. It took a look. These numbers grow very fast. They get very big. So it was very hard by hand to test whether or not such a number was prime. And it was finally discovered that 2 to the 2 to the 5th plus 1, which is 2 to the 32nd power plus 1, which if you write it out is some big number, is composite. Any questions about this? Okay, let me do one more problem. There's a really a skill, an art form in learning number theory and being able to apply the basic results to obtain new results. So in section 1.5, this is problem number 4. Sorry, problem number 8. So this is to modify the proof of theorem 114, which is Euclid's theorem, to prove there are infinitely many primes whose remainder is 3 when divided by 4. That means of the form 4k plus 3. Remember, in Euclid's theorem, we proved there are infinitely many primes. But except for the prime number 2, every prime is odd. So we could also say Euclid proves there are infinitely many primes of the form 2k plus 1, plus every prime numbers of the form 2k plus 1, every odd number. So in this result, we want to show that for numbers of the form 4k plus 3, a very special form, there's still infinitely many primes. And remember the trick in Euclid's theorem. We took a finite group of primes, P1 up to P sub k, multiplied them together, say up to P sub L, and added 1. And we looked at this number and said this number is divisible by a prime, and it couldn't be one of these. So I'd like to do something similar in this case. And why are we looking at 4k plus 3? So every prime P bigger than 2, it's odd. So if you divide it by 4, you get a remainder. If the remainder were 0, this number would be even, and it's not a prime. If this number were 2, this would still be even, and it's not a prime. So when you divide by 4, if you divide a prime by 4, you either get a remainder of 1 or a remainder of 3. Now, suppose I multiply together two numbers that are of the form 4k plus 1. So I have a number 4k plus 1 and a number, let's say 4l plus 1, and I multiply them together. I get 16kl plus 4k plus 4l plus 1. This is 4 times 4kl plus k plus l plus 1. This is 4m plus 1, where m is this number. 4kl plus k plus l. So if I take a number of the form 4k plus 1, and I multiply it by an integer of the form 4l plus 1, I end up with an integer that can also be written in the form 4m plus 1. So if p sub I is 4k sub I is of the form 4 times something plus 1. So if p sub I is 4k sub I plus 1, for I going from 1 up to r, let's say, then if I multiply together p1, p2 up to p sub r, when I multiply numbers of the form 4k plus 1, I get a number of the form 4k plus 1. So my conclusion from that is the following. If n is a number of the form 4k plus 3, and n is a product of prime numbers, then at least one prime p sub I is of the form 4k sub I plus 3. If n is 4k plus 3 in that form, and you write it as a product of prime numbers, all the primes have to be odd, because this is an odd number. So they're all the form 4k plus 1 or 4k plus 3. If they were all 4k plus 1, the product also would be 4k plus 1. But n is not 4k plus 1, n is 4k plus 3. So at least one of these primes is of the form 4k plus 3, which is the same as 4k sub I prime minus 1. If you can write a number in the form 4k plus 3, you can write 4k plus 3 is 4k plus 3 is 4 minus 1 is 4 times k plus 1 minus 1. So to say a number is of the form 4k plus 3 is the same as saying it's also the form 4k minus 1. Those are equivalent statements. So suppose I let P1, P2 up to P sub R be primes of the form 4k plus 3, or I'll write them as 4k minus 1. That n, I want to be a little bit tricky here. I want to take the product of all these primes, multiply it by 4, and subtract 1. So n is of the form 4 times something minus 1. And the something is the product of all these r primes of the form 4k minus 1. So n is odd. N is divisible by some odd prime p. In fact, if n is of the form 4 times something minus 1, it has to be divisible by an odd prime, let me call the odd prime q, which is also of the form 4k minus 1. Because if this were just a product of primes of the form 4k plus 1, the product would be as well. So q divides n, which means q cannot be equal to one of these primes, because then it would divide the difference, which is 1. So q is different from p sub I for all I going from 1 up to r. And that means we're done. Given any finite set of primes of the form 4k minus 1, we can prove the existence of another prime of the form 4k minus 1, different from the finite set you started with. And so this implies the number of primes of the form 4k minus 1 has to be infinite. That is the proof. So these are very, very nice and very important problems, and worth spending a lot of time trying to understand. There's a great deal of number theory involved in this. Any questions about this? So I'm happy in our next class on Wednesday to answer any questions you might have about anything we've done or any of the homework problems. And then we will have finished what we're doing in chapter 1, and we'll begin to study chapter 2 on congruences. Any questions? We also have a problem session this evening at 7 o'clock if you have questions. And if you have questions but you can't make the 7 o'clock session, then send me an email and we can arrange a time when we can meet on Zoom privately. Okay. If there's nothing else, then we are done for the morning.
I have one question.
Go ahead.
It was about I believe it was section. I believe it was section 1.2, I think.
Okay.
Let me make sure. Yeah, it was section chapter 1, section 2, question 25.
This is the
Not 20, I
question
mean not
about
25.
subgroups of Z.
18, sorry.
18. Okay. So section 1.2, number 18. Number 18? So
Yes.
we're looking at rational numbers of the form a over 2 to the k. We're looking at this. Is this the problem?
Let me see. Let me go to the section. 18. Yeah, rational numbers.
Okay, of this form. So a can be any integer, and the denominator is any non-negative integer. So we're looking at all fractions whose denominators are powers of 2. Like you might have 7 over 32 plus 109 over 128, right? This is a fraction where the denominator is a power of 2. This is a fraction where the denominator is a power of 2. If you add them, let's see, 64, 128. If I put this over a denominator of 128, this is, I multiply by 4, I have 28 over 128 plus 109 over 128. And I can add them, and I get 137 over 128. So here I have two fractions of this form. This is just an example, and I add them, and I get another fraction of this form. And in general, so I want to show this is prove this is a subgroup of Q under addition. So suppose I have two numbers, a over 2 to the k and b over 2 to the l, and I want to add them. So let's suppose k is greater than or equal to l, right? That is, if you have two numbers, one's bigger than the other. So I can put this over a common denominator. This is a over 2 to the k. And what do I multiply L by to get 2 to the k? I multiply by 2 to the k minus L. Then I have to multiply the numerator by 2 to the k minus L. So I've taken this fraction and I've multiplied the numerator and denominator by 2 to the k minus L. Now this denominator is 2 to the k and this denominator is 2 to the k. So I can add fractions with this same denominator. This is a plus b, 2 to the k minus L. So let me call this set G for the moment. If I take two elements of G and I add them, I get another element of G because this is some integer over a power of 2. And I can also subtract. I just get minus sign. So this set is closed under addition and subtraction. And 0 I can write as 0 over 2. So that's also in the set. So this set contains 0 is closed under addition and subtraction. That means it's a group. I mean, the crux of it is really just showing this. If I add two or subtract two numbers of the form, I get another number of that form.
Is that a plus and minus?
Yes. Now, is that okay?
Yeah, I understand. Thank you.
Okay. Okay, well, next class on Wednesday. Bye.